integration basics or antiderivative basics. What is an integral? What is an antiderivative? Well, the notation looks like this. And then you have some expression. To better understand integrals and what they are, it's best to first look at basic derivatives. So looking back to Calculus 1, where you're asked to find the derivative of something like x squared. Pretty straightforward. We all know that that's just 2x. But what if you are asked to find the derivative of, let's say, x squared plus, I don't know, 9. We also know that that's just 2x. Same answer as before. Looking at a bigger number, let's say we're asked to find the derivative of x squared plus, I don't know, 1 million. We also know that that's equal to 2x. But what does this mean for integrals? I'll just erase these two, get these out of the way to give us some room here. I'll leave the first one. What does that mean for integrals? Well, let's say that we're trying to find the antiderivative or integral of the 2x. And give yourself a minute here to think about what this would be, and you might want to jump up and say, okay, if the derivative of x squared is 2x, then that means that the antiderivative of 2x is going to equal x squared. But that can't be, and I'll show you why. How do we know that the integral of 2x doesn't equal x squared, the x squared plus 9? And how do we know that it doesn't equal the x squared plus 1 million? How do we know it's not x squared plus 500,000? So it has to be x squared, but we don't know the other constant. And how do we show that? We just put c. We don't know the constant, there's no way to know the constant. So the answer would just look like x squared plus c. This could represent anything. So with that one example out of the way, let's try another here. And these are just basic. So let's say that we have we're looking for the integral of I don't know, 3x squared. If you think about this one for a minute, you can see that this used to be x cubed. We used the power rule, put the 3 in the front, and then took 1 away from the exponent. So the answer would be x cubed, and then you can't forget the plus c. How about a trig example? So let's say you're looking for the antiderivative of cosine, a nice easy one. Cosine x. If you think back to Calculus 1, the derivative of sine is cosine. So we know that the integral of cosine x is going to equal sine x, and then we add in the plus c. make a little bit more room here for us. I would just tap clear, but every single time I tap clear, it just takes the nice dark background away and leaves me with a white background and gets rid of this. Okay. Looking at another example. Let's find the antiderivative of e to the x. You may have guessed it's e to the x plus c. Another good one to know, the antiderivative of secant squared x. You might remember that the derivative of tangent x would equal secant squared x. So our antiderivative would be tangent x plus the c, plus some constant. I'll do out a couple more examples, but instead of doing these, let's try to kick it up a little bit. Do something a little bit more challenging. So we're looking for the antiderivative of, I don't know, let's say we're looking for e to the x over 2. At first glance, this looks daunting, but if you separate this out, we have 1/2 times e to the x. But this doesn't do anything for us until you know the rule that we can actually take this constant out. You can actually move this constant. There's a rule that says you can move this constant to the front of the integral. So we can rewrite this as 1/2 times the integral of e to the x. So our final answer would be 1/2, and the derivative, the antiderivative of e to the x is e to the x, and then we just add in our plus c at the end. Pretty straightforward. Here's one that you're going to need to know. Looking for the integral of secant x tangent x. And I'm probably writing a little big here. Oh, that's fine. Secant x tangent x. That should ring a bell. That's actually one of our common trig derivatives. So you may remember that the derivative of secant x is secant tan. So that would mean that the integral of secant tan is going to be secant x plus c. Always have to have that constant at the end. There's a couple others that are good to know. So let me just get rid of this here, and I'll get right to it. One that you're definitely going to need to know, and I guarantee that you'll see this problem all through Calculus 2, or a different form of it. You'll be asked to find the integral of 1 over x. Or a different form of that could be some other number over x. And this is a common integral. You might remember that the derivative of the natural log of x is actually 1 over x. So the integral of 1 over x is going to be, and this is where it gets a little different, the natural log try to rewrite that better here. The natural log of the absolute value of x plus c. Always have to have that plus c there. Alright. Let's do another one. This will be the last one. This will be the last one for the video. Let's say we've got, you're looking for the integral of, and I'm just trying to make some better ones up that aren't in the book. Let's say we've got, I don't know, some trig expression here. Make it look like it's tough, but it's actually not. Cosine x over, let's say 10. Well, thinking back to the e to the x problem, where there was a constant in the front, we can rewrite this as, 1/10 times cosine x, the integral of 1/10 times cosine x. We can take this constant out, put it right in front. Definitely want to get in the habit of doing that because it makes the problems look 10 times easier. So we have 1/10 times the integral of cosine x. And I'll try to squeeze it in down here at the bottom. We know that the antiderivative of cosine x is sine x because the derivative of sine x is cosine x. So the answer is 1/10 sine x plus c. And that's your answer to that one.